Shahira.
Hi, I'm Nabila.
Hi, I'm Chu.
Hi, I'm Shri.
Hi, I'm John.
Guys, do you know what is electromagnetic induction?
No.
Electromagnetic or magnetic induction is the production of an electromotive force EMF across an electrical conductor in a charging magnetic field.
Oh, that's interesting. Can we know more about it?
Let's go!
Electromagnetic induction. In this part, we will learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or wooden cylinder to form a coil in the form of solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary. The pointer of the galvanometer deflects toward the right when the north pole of the magnet is moved toward the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The deflection increases if the magnet is moved away with a greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction. The galvanometer accordingly turns toward the left. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. There is a few factors leading to increased current in the coil. First, by using a strong magnet. Second, increasing the motion of the magnet. And third, increase the area or the number of turns of the coil. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So, the galvanometer shows no deflection. But when the magnet is moved toward the coil and vice versa, the magnetic flux changes and the EMF is induced in the coil. The magnitude of the induced EMF is directly proportional to the rate of the changes of the magnetic flux linked to the coil. There is two factors affecting the magnitude of EMF, which is changes in magnetic flux and time in which flux changes. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux.
Now we are going to discuss the Faraday's law of electromagnetic induction. Let's take a simple coil and connect it to a battery. Here is the magnetic field around it, and take another coil connected to a galvanometer. Now we hold the second coil nearer to the first coil. A more specific way to say that the second coil is under the influence of the magnetic field of the first coil. Then we can observe that no voltage occurs to the second coil and there is no deflection in the pointer of the galvanometer. This means that no voltage is induced in the second coil. Now, we move the second coil inside that influence of the magnetic field of the first coil. We observe during that the movement of the second coil, the pointer of the galvanometer deflects. This indicates that some voltage has induced across the second coil and the pointer deflects. Okay, let's move the first coil to the second coil. In this case, we observe that there is voltage induced across the second coil. So, in the first case, there is no voltage is induced. However, in the second and the third case, the voltage is induced. This is fulfill the Faraday's first law of the electromagnetic induction, which says that when a conductor links with a changing magnetic flux, there is voltage induced in it. Okay, now we move the second coil faster inside the influence of the magnetic field. We see that the faster the movement, the faster the deflection of the pointer. Same things happen when we move the first coil faster. Therefore, the rate of change of the flux linkage increases, the induced voltage increases. This is fulfill the Faraday's second law of the electromagnetic induction.
Do you know any project to make us understand better?
Yes, I do.
Wow, let's have a look.
Let's go!
Making of a DC motor. These are the equipments and tools used. Equipment and tools used are pliers, scissors, paperclip, magnet, battery holder, copper coil, cardboard, sellotape, and glue. The first step is we are going to be using two paper clips. The paper clips are used for stand. So the first thing what we do is we have to remove the insulator of the iron. Once removing the insulator of the iron, we have to bend like shown in this video such a way to create a stand for both of the paper clips. For the next part, we are going to be using the battery holder and the battery to connect both the positive and negative to each of the paper clips. The following step, we are going to be taking both of the paper clips and we are going to be sellotaping it on the cupboard. The cupboard acts as a base. The following step, we will be doing the copper coil. We turn it around for 5 times to come up with the copper coil. Then we use it to tighten it up, making both ends has the same amount of length. Then, by using a sandpaper, we will use to rub it off at both of each end of the copper coil. Finally, we will place the copper coil on both of the paper clips at each end and we will place a magnet under it. This is the output. Wow, nice project!
Can I know why the coil rotates?
Yes, let me explain.
So basically, just to explain for how this mechanism works for our project, the assignment we did for EMT. So you can see here the picture is show is where you see the current carrying conductor on both sides of north pole and south pole of magnet, and the output is the acting force on it. Alright. Okay, now you can see two of the even detailed picture. The DC motor contains current carrying armature which is connected to the supply and to the commutator segments, and the brushes. The armature is placed between north and south pole of a permanent or electromagnet in an aluminum model. One single turn of the conductor is placed between two opposite poles. If we start to supply DC via commutator system, current will start to flow as the positive terminal of a battery is connected to the left conductor of a turn and a negative terminal is connected to the right side of the turn. So as we see in the model, north pole of the magnet is placed near left side and the south pole is placed at the right side. Right, doctor? So here the turn is basically where what happens is the current and the left side flows inward and the current on the right side flows outward. Okay, as you see the conductor is carrying current and they place in the magnetic field. Both of them experience a mechanical force acted on them, right? And the direction of a mechanical force can be easily determined by applying prime left hand rule. Let me show you how to use them. So basically, applying prime hand rule is to do is spread out the thumb forefinger and the second finger, so they are at all 90 degrees to one and another. Alright, then this is how basically it should look like. So its main application is that if the forefinger is in line in the long direction of the magnetic field from the north pole to the south pole, and the second finger is lined along direction of the current and left side conductor. Then the thumb indicates direction of mechanical force actually. Alright, then you can see just a simulation of idea of how the force happening that we show you. Then similarly, if the forefinger is in a long direction of the magnetic field from north pole to south pole, right, and the second finger is aligned along the direction of current and right side conductor, then the thumb indicates the direction of a mechanical force. Due to this, what happens is the upward and downward force is on turn. So one torque is produced. Therefore, when the turn happens, rotates on the clockwise direction as shown above, you can see that makes the coil to spin. Alright, okay, so that's the best way to understand. So after the rotation of the turn comes to a vertical position in respect of the magnetic field. At this position, there is no current in the conductor because the turn, the conductor and the brush rest between two commutators are just a constant state. So basically here we can conclude there's no force acting on the conductor by due to the momentum of inertia. The turn continues to rotate and comes horizontal again. So the position of the conductor has been changed here, that meaning that the conductor which was previously in the left position comes to the right position, and which was previously in the right position comes to the left position. That's how it moves clockwise. Alright, so at this position we can determine mechanical force with the application of Fleming's left hand rule. Okay, so let's see how we do that. So basically it's just that we spread out, as initially I said, the thumb finger and the second finger, so they are 90 degrees to one another. Then what happens is we can see that if the forefinger is in line in the direction of the magnetic field, that is from north pole to south pole, and the second finger aligned in the direction of a current in the left side conductor, then the thumb indicates the direction of the mechanical force. Okay, so this is clearly upward here, and you also can say if the forefinger is in line in the direction of the magnetic field, that is from the north pole to south pole, and second finger is aligned in the direction of the current in the right side conductor, then the form indicates direction of the mechanical force. This is clearly downward here. So therefore, during this, there will cause upward and downward force that tends to rotate in clockwise direction. From this explanation, we can conclude that here in this model we can see that whichever conductor comes near the south pole experiences upward mechanical force, and near the north pole it experiences a downward mechanical force. So doing this continuously, the force of mechanical will rotate even if the battery is not connected. Alright, so this is how the application works, doctor. And the rotate has the same principle like this in the elementary model that we did for our EMT assignment. Alright.
Oh, that's why the coil rotates.
Now, you guys know more about electromagnetic and Faraday's law, right?
Yes.
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 We do.